All right, in this video we are going to start optimizing our code, but before we do that, let's write a benchmark so we actually know how much our changes will improve the speed. So here we are in our benchmark code, and we are going to say use Gray Scott. We want to use the naive update. Yes. Let's actually just do that. And let's also use the UV because we'll need that. All right, we don't need this stuff because we don't really care about how fast we can do this dot product, but it was kind of fun stuff. So I'm actually going to save it down here. All right. So what we're gonna do is we will bench a function. And this one is the naive update. And then we have some preparation code. Let's make a UV. So UV zeros. And we need a size, so number of columns. Let's say it shouldn't be too big, but it also shouldn't be too small. Let's try 200 by 200 rows and columns. And then we want to fill something in here. So let's make it mutable. So for row and 0 to rows, do something. Number of columns. Let's see, we have U here. So let's say row column. Maybe that is just row as F32 multiplied by column as F32. Why not? Something like that. And the same thing for the V. And we actually need two of these guys. Let's call it next. I will see that later. And this one maybe it's minus. Whatever, just something so there's like non-zero values almost everywhere. All right, so now we have the naive updates, and it takes a UV and it takes something to write into, something like this. And this is what we want to benchmark. So we have to do this thing where we say, okay, so for some number of iterations that benchmarking framework decides, run this. And we also need the options. So let's go ahead and say use Gray Scott, update options. Like that. What are those update options? They are something. So we need feed rate. I don't know. Maybe we can just pick the defaults. So it wants this, it wants for the kill rate, this thing, and the delta T default value is 1, right? So we have that, and then we need to put here. All right, let's now try to run that benchmark. All right, so here we are. 2 milliseconds per iteration. So maybe let's make it a little bit bigger. So I think we can try this. All right, here we go. So now I think I kind of like it. So we have 4 million points. It takes about 226 milliseconds per iteration. The benchmark runs in a reasonable amount of time. And I think this is a good reference to have. All right, so now we need to do this thing, this first optimization, which is called regularizing. So we don't really have a profiler. Maybe I should look into that, but we don't have that. But what he says is that, okay, actually, we're spending a lot of time doing this computation, which is computing which indices we need to access. So this type of algorithm, it looks at a certain point, like this O, and then it collects data from the neighboring points. I hope that drawing made sense. Actually, give me a second. So here I can make an actual drawing for you. So we have this type of algorithm works on this point, for example. This is the point I want to find out what is the next value for that point. What it does is it looks at the neighboring points like this, and actually in our case it looks at all of the 8 neighbors. And we get an index. We know what the orange index is, that's known, but then we have to compute the other indices. And he claims that the author of this course claims that that is taking a lot of time. Obviously, we haven't tested that because we don't have a profiler for that. But you can imagine that, okay, it is spending a lot of time doing these subtractions and additions and things. Like, they are not really necessary because you kind of already know. So there's this nice thing in ND-array which is called windows. So in our iteration right now, we are just like going point by point. But in the window, so we go like this one, that one, that one, that one, that one, something like that. But ND-array has this special iterator where you can go over a window. So you get all of these at once, and then it goes to the next one. And I think you can also specify the overlap. I think it by default actually it overlaps them, which is really what we want. Problem with that is that you don't really handle this corner point, because in the corner point we really want this window, which like go, if you imagine the gray thing is the area of the world. We kind of want to look outside the world, and you have to decide what do you do when you look at a point outside the world. And in our case, we'll just put a 0. But anyway, that's something that has to be handled separately when we do this window iterator. But the benefit of the window iterator is that you don't have to do these calculations that we're doing here. Like, you don't have to calculate what are the neighboring points. That's just given. So let's see what we can do. We have our naive thing. So let's make one that's called windowed. The windowed, and put that in here. Register it. Windowed. Maybe we'll do something like this. Update implementations. All right. So we want to do something kind of similar to this. So let's copy that. So we have something to start from. But anyway, what we want to do is we want to say start view and windows. And this one has a window size. And in our case, we want 3x3 window. So what we can do is we can try to use this azip. And here we want a reference to the output element. We need to put that in parentheses. One references to the output elements. Then we want the windows like that. I think actually, just for symmetry, let's call these things like window window, common window U. All right, so there we have some windows. Now the problem is that this array, it doesn't have the same number. These two arrays doesn't have the same number of elements as these window arrays, because this one, the windows, doesn't include the boundaries like we talked about. So what we need to do is actually to do a slice where we only take the center elements. So slice center elements. Now what is the center element? That's something we have to define. And we can use the slice macro, S macro. And we need to do like, because it's a 3x3 window, it's actually only going to skip one at each edge. So if we go back to the drawing, this amazing drawing I have going here, imagine again that the gray is the array. So we want a 3x3 window. It kind of looks like this. And it's going to start one off from the edge, as you can see. That's the closest you can get to the edge. And it's going to end one off on the edge. That's also the closest it can get. So it's going to be 1 to shape 0, -1. 1 to shape 1, -1. I think that should do it, except that the way I index this is wrong. So we have to do shape 0 and shape 1. All right. So here we go. We have our function here. So this one it doesn't like. Maybe this one has to be slice mutable. Okay. And this one doesn't like that either. So I suppose we have to write not 3, but 3x3, which makes a lot of sense. Okay. So now we have that. And now we can say, okay, the center U is basically this, or, well, that's not how you do it. You have to wrap it like that. Or we have this thing in our constants called stencil offset, which is supposed to point to the center, so we can actually use that stencil offset. And we also have the V, because the center concentration has kind of like a special meaning. All right. Now I don't remember what we actually have to compute. Okay, so this is like a little bit difficult to see what's going on. Let's put these two on a buffer like that. Okay. So this one is basically taking the window of U and it's zipping it with the window of V. So we have to do something like window U. Can that be zipped? Maybe we want to use the zip construct. So we can say zip from window U and window V, and then we can say for each. And what do we want to do there? We basically want to do this kind of operation where we're multiplying by the weights and then summing it all up. But also we want to subtract the V, the center value from it. So we have to do something like so actually, what do we have here? Let's see. I think we should get two things. So that one doesn't let us do that. What's the problem here? Okay, so for some reason you need that. That didn't work. Okay, so what is this? This is not correct. Okay, we have these two numbers. what do we need to do? Like, what's the best way to write this? Do we have like a sum, a fold? We do have a fold. So I guess that makes a lot of sense to do a fold like we do in the other one. And we need an accumulator, but that's just a number. Then we need a function. So we have the a and b again, which we really should call maybe u and v. This one is a reference, this one is not a reference. Not really is there, like, do we need another one? Can I just keep adding? Okay, that's kind of weird. That's kind of weird. Okay, let's just look at the way he did it, because I don't know anymore. Okay, so here we go. We have the center. We have here. Okay, so what we actually, it's a good idea maybe. So we can also zip it with the stencil weights. Not sure you can do this because this has to be, potentially it has to be a NumPy array, not an ND array, not NumPy. But we have these, and then we should say, be able to say, no, it doesn't like that. Does not like that. Okay, so let's not do that. Let's just do, let's turn it into an iter. Let's zip it, this one, and zip that again with the stencil weights. The way he's doing it. And this one, he wants to flatten it. Okay, fair enough. Anyway, and then it's a fold like we had before. And it's the same kind of fold. Let me put that down here actually. So let's fold it, and we need the initial value, which is going to be two things. Then we have the accumulator, and then we have a bunch of stuff. Actually, we can unpack this like that, and then we have this crazy thing. So let's just call it u, let's call it v, and then let's call it weight. And I think that should do it. So we have some floats, we have, here we can just return the same thing, so it compiles. Okay, great. And what we want to do is we want to do the same calculation here. We want to say weight times u minus center u. And the same thing here, except it's v. I think that should match what he has. Great. And then the rest of the computation is the same. Except that this thing should return something. So let's say full u, full v. And then we do this. Then we do this. This is supposed to be center now. Center, center. All right. It seems to compile more or less. Now the thing is, we're only now operating on the center, so that's not so good. We need to also handle the edges, so everything is covered. So let's say we have like upper edge, and at this point I think I want to just import this as macro. So this one is all, let's say, okay, it's the upper edge. It's the upper edge, which means this is 0, and then we have everything there. Then we have say the lower edge. Okay, it should be shape 0, but probably -1. Then we have the right edge, and that's everything here, but then it's 0. So that's probably left edge. And the right edge is this thing. Then we want to do the naive computation, but over those. So let's try to set up our function here. So it's kind of something like this, right? But instead of windows, we're going to slice, and it's not mutable, like upper edge. I'm going to try to do it in an ugly way, like this, and this one we can change to upper edge. And here we have just center U. All right. And then we need to do this operation. And we also need the indices, so that's a little bit annoying. Can we just copy that? Will that work? Seems like it's not going to. Because this thing has some specific dimensionality. It's 1D, which makes a lot of sense. So basically here it should be the column. Okay, so that compiles. And we can even say plus is, the row is always 0, and then we can copy everything else, and that should be correct. We don't have the array 2, so we're going to copy that. And it doesn't like this, so I have to say that this is, do I really have to say it's the U size? Some kind of compilation error. And these guys, let's just call them this. All right, so this would be one way to handle the edges. Then we need to run that 4 times. So actually, we should probably pull that out somewhere into a separate function. So let's say handle edge, and it's going to take 2 UVs. Actually, it's probably going to have the same signature, but so let's go up here and yank that. So this is what we're going to do. We're going to grab this, handle edge. Another thing it's going to do is it's going to get the slice, I think. Let's do that. So there's some crazy crazy type, which is a bit annoying. It is a bit annoying. So maybe we just make it a little bit of helper. So upper, lower, right, left. So we're going to take here an edge. And then we're going to say edge is equal to match the edge. And if it's the upper, basically, let's get this stuff in here. Maybe we can write a macro. So we delete let. We jump to this one. We delete that. We go here. We say edge colon colon. Then this thing we highlight and we turn it into an uppercase. We go to the equal sign. We do this. And finally, we turn the semicolon into a comma. We go to the next line. And that's our macro. Okay. Then we need the shape. Let's get that on here. Oops. So now we have the shape. Another thing we want to do is, let's say row output. So we can say, okay, if we are iterating over the upper edge, then this should be false. We're not outputting to the row. Same thing here. These guys is actually true. True. And this one we're gonna call out index. And now we have this one. So the out position is if row output, it should be out index and 0. Otherwise, it should be 0 and out index. So it's horrible formatting, and these guys should just be edge. And we cannot auto format it because it's inside of a macro, which is a little bit unfortunate. All right. It's complaining something here. Okay, it's called out. Called it out index. So that should handle that. Then here, when we've calculated the center stuff, we can say, okay, actually handle the edges. Use the same options. Start, end, and then we can say do the upper and the rest. There is one issue with this, is it will actually do the corners 2 times each, but it doesn't really matter overall. Great, great, great. So what I would like to do is actually to write a test that we implemented this correctly, because maybe it's super fast, but it does something completely wrong. So I want to say use create naive, and I can also use super, I guess. Can I just do create window? Then we have a test here, and let's call it matches naive. So then I think I want to go into the benchmark. And I want to steal this initialization. But here we're not going to use that many, we're just going to use 200. We have some non-trivial values. We should actually have 2 outputs, so we can check that they're the same. So like this. And we should also use create UV. Great. And also the update options. Great. So what we're going to do is we're going to say, okay, run the windowed update with these options. And this is the starting point, and put it into this thing. This has to be a reference. This has to be a mutable reference. Do the same thing, but now for the naive. And then we want to iterate over everything. And maybe there is like an empty array, like in NumPy. Probably not. Okay, so what we're going to say is this one, a row column, that should be equal to this guy. But instead of window, of course, it should be naive. And it should be U, and U, and V, and V. All right, let's run the test. It may not work. Okay, so it didn't work. That's great. Because we're writing into the window twice. So of course it wouldn't work. Okay, so that's good. We actually have some kind of error. That's interesting. I wonder where it fails. Can we just do something silly like this? It actually runs for like the full first row is the same, it looks like. But then the next one, the second row, it fails. And I think I found another bug. I don't think this is what's causing it, but we should also have like out. What do we call this? Let's just call it out. And what I want to do is I want to put that here, because in some cases we have the output to 0, in some cases not. And in this case, what is the output row? Okay, it should be 0. And in this case, it should be this. In this case, it should be, what is the output column? It should be 0, I think. In this case, it should be this. And now let's run the test again. That actually fixed it. Okay. Did it? Yes. Okay. So that fixed it. So now we have an implementation that exactly matches. And of course we can try like different, at least for this input, but it would be extremely lucky if we created some kind of input where two algorithms that didn't do the same thing matched exactly. So I think this is a fairly good test. I mean, we could make it more complicated. We could do something like, let's say this is actually sine, but still it's exactly the same. Okay, so now we have those two. Let's go ahead and make a benchmark. It's basically the same, so probably there's some way where we can reuse the code. Maybe if I just pull this out, can I do that? Pull it out here, and this one is the same, but here we just do windowed, and we have to get that up here, windowed. Does that work? It's not complaining so far. So let's run the benchmark. All right, here we are. So the benchmark is run. The naive update takes again like 225 milliseconds, and the windowed update, which I forgot to call windowed update, which I'll just do here, it takes 100 milliseconds. So speed up of a factor of 2 just by doing this windowed thing, which is kind of surprising to me, but I guess it makes sense. All right, But that's going to do it for this video. In the next video, we're going to look into something very cool, CMD. All right, but until then, have a good time and bye-bye.